Welcome to another episode of learning. I thank each one of you for watching my videos. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of June 2023. The given question is from group theory and it is related to subgroups of a given group. This question is from the part C, which is a multiple select question. There can be more than one answer. It carries 4.75 marks. The question ID is 704083. This question is suitable for all these examinations. Right. The given question is, which of the following statements are true? We are given four options. Option 1. If G is a group of order 244, then G contains a unique subgroup of order 27. Option 2. If G is a group of order 1694, then G contains a unique subgroup of order 121. Option 3. There exists a group of order 154 which contains a unique subgroup of order 7. Option 4. There exists a group of order 121 which contains two subgroups of order 11. And read the options 3 and 4 carefully. They say there exist groups of certain orders. Let's now discuss the solution of the problem in detail. We take the first option. Option 1. If G is a group of order 244, then G contains a unique subgroup of order 27. So we have a group G of order 244. Right. The question is, will the G contain a unique subgroup of order 27? To have a subgroup of order 27, by Lagrange's theorem, this 27, the order of the subgroup, must divide the order of the finite group. So that means 27 must divide 244. Is it so? No. 27 does not divide 244. Therefore, G has no subgroup of order 27. There is no question of uniqueness. Assume that G has a subgroup H of order 27. By Lagrange's theorem, order of H divides order of G, that is 244. This means 27 must divide 244, which is a contradiction because 27 does not divide 244. Therefore, G has no subgroup of order 27. Therefore, the option 1 is not true. Right. We move to the next slide for the option 2. Option 2. If G is a group of order 1694, then G contains a unique subgroup of order 121. So, we have a group G and its order is 1694. The prime factorization is 2 into 7 into 11 square. We are trying to apply Sylow's theorems. Right. Now 11 square divides order of G and 11 cube does not divide order of G. Therefore, by Sylow's first theorem, G has a Sylow 11 subgroup, say H, of order 11 square. We apply Sylow's third theorem. By that, N11, that is the number of Sylow 11 subgroups of G, is of the form 1 plus 11k. N11 is of this form and N11 divides order of G, that is 2 into 7 into 11 square. And further, N11 is of the form 1 plus 11k divides 2 into 7 into 11 square. So 1 plus 11k obviously does not divide 11 square. Therefore, 1 plus 11k divides 2 into 7, and that is 1 plus 11k divides 14. And keeping the various non-negative integer values of k, we get k. For k is equal to 0, it is true, 1 divides 14, and go on verifying for the other values, and for k is equal to 1, it is 1 plus 11, 12, 12 does not divide. For k is equal to 2, 22 plus 1, 23 does not divide 14, and as k grows, this will become bigger than 14. Therefore, it is sufficient. So, k is equal to 0 is the only solution. When k is equal to 0 is the only solution, N11 is 1. So, that means there is a unique Sylow 11 subgroup of G of order 11 square, that is 121. H is the unique subgroup G of order 11 square is equal to 1, 2 into 1. Because it is unique, it is a normal subgroup. Of course, that is not needed now. So H is so there exists, thus G has a unique subgroup of order 121. So G contains a unique subgroup of order 121. We have achieved that. Therefore, option 2 is true. Right. Option 1 was false and option 2 is true. We move to option 3. There exists a group of order 154 which contains a unique subgroup of order 7. So in this, you have to show the existence of a group of order 154 which has a unique subgroup of order 7. Right. Here we have to show that there is a group of order 154 which has a unique subgroup of order 7. Recall two results from abstract algebra, that is group theory. That is, given a positive integer n, you always have a group like Zn. Addition. Zn is a group of integers modulo 11 under addition modulo 11. Right? So for n is equal to 154, you also have a cyclic group Z154. For a cyclic group of order n, when d divides n, there exists a unique cyclic subgroup of order d. So for each divisor d of n, you have a unique cyclic subgroup of order d in Zn. These are the two results. You recall, for each n belongs to n, we have a group Zn which is cyclic, and for each positive divisor d of n, the group Zn has a unique subgroup of order d. So for n is equal to 154 and for d is equal to 7, so the result follows. Thus, there exists a cyclic subgroup cyclic group Z154 of order 154, and 7 divides 154. By the above result, Z154 has a unique subgroup of order 7. Thus, we have proved option 3. So, there exists a group of order 154 which contains a unique subgroup of order 7. That is true. Right. We move to the next option. Option 4. There exists a group of order 121 which contains two subgroups of order 11. Existence of a group of order 121. 121 is what? 121 is 11 square. 11 square. So, and every group of 11 square is a billion. Right? For an abelian group of order 11 square, they are isomorphic to either Z11 square or external direct product of Z11 with itself. Yeah. We argue now. We have a group G. Order of G is 121 11 square. Clearly, G is an abelian group because every group of order P square, where P is a prime, is abelian. P, the 11 is prime, therefore 11 square. With that order, you have a group which is abelian. And for abelian groups, if G is an abelian group of order 11 square, G is isomorphic to either Z11 square or Z11 plus circle Z11, the direct product of Z11 with itself. Why these only two? For 2, we have to look for its partitions. This I think I have already told you in the last lecture. For 2, the partitions are 2 plus 0. Corresponding to that, you get Z11 square. 2 is 1 plus 1. Corresponding to that, Z11 plus circle Z11. These are the only two partitions. Therefore, G is isomorphic to either Z11 square or Z11 plus circle Z11. Now, out of these two, what is that group which contains two subgroups of order 11? That's what we ask. We ask a question, is it Z11 square? Here Z11 square is cyclic because it is Zn. Zn, it is cyclic. And Z11 plus circle Z11 is abelian but not cyclic because the highest order of any element in Z11 plus circle Z11 is 11. It's not 121. Therefore, it's just an abelian but not cyclic. Right. Now, note that Z11 square has a unique subgroup of order 11. Why? Because 11 divides 11 square. For each D, for each divisor D of n, we have a unique cyclic subgroup of order D. So, 11 divides 11 square, therefore, and Z11 square is cyclic, therefore, it has a unique subgroup of order 11. But we want two subgroups of order 11. Therefore, this is not the group that we are looking for. Perhaps it may be Z11 plus circle Z11 is abelian but not cyclic. Now, consider Z11 plus circle Z11. And in this group, let H1 be the subgroup generated by the element 1, 0 belongs to Z11 plus circle Z11. Now 1, 0 generates what? 1, 0, 1, 0 plus 1, 0, 2, 0, 2, 0 plus 1, 0, 3, 0, etc. 10, 0. And add one more time, it is 0, 0. It's not dot, it is comma. So H1 is the cyclic subgroup of Z11 plus circle Z11 generated by 1, 0 and its order is 11. So we have one subgroup of order 11. The other H2 is a cyclic subgroup generated by the ordered pair 0, 1. So this also generates 0, 1, 0, 2, 0, 10, 0, 0. Its order is 11. So thus we have two subgroups, cyclic subgroups of order 11 for Z11 plus circle Z11. That is sufficient for us. How many? We are not interested right now. So H1 and H2 are cyclic subgroups of Z11 plus Z11 plus circle Z11 of order 11. This shows that there exists a group of order 121. What is that? Z11 plus circle Z11, which contains two subgroups. How many we are not interested? Two are there, two subgroups of order 11. Agreed. So that means option 4 is true. Option 4 is true. So summarizing all the options, the answer to this question is options 2, 3 and 4. Option 1 was not true. That is the detailed discussion of this given problem from group theory, which is related to subgroups of a given group. Agreed. We have asked a question. How many, for Z11 plus circle Z11, how many cyclic subgroups of order 11 are there? We have shown only 2. How many? That was the question. And the answer we know. Therefore, I will revise your option 4. We revise option 4. Let us say, think. We revise the option 4 and discuss the case. So, an option is revised. That is the fourth option is revised. 4 star we said. There exists a group of order 121 which contains 12 subgroups of order 11. Previously, we have shown 2. That is sufficient for us because the option was only 2, about 2. Now it says 12. Is it true? Is it true? Now, we have shown there is Z11 square and Z11 plus circle Z11. And Z11 square has only one subgroup of order 11 because Z11 square is cyclic. Therefore, that's not the candidate for us. So, we look for Z11 plus circle Z11. Right. Now, how many cyclic subgroups of order 11 are there? Here is the number of cyclic subgroup of order n in a finite group G. Group order is not given, finite group G. How many? So the number of cyclic subgroups of order n in a finite group G is given by, is equal to total number of elements of order n in G, total number of elements of order n in G divided by number of generators for each cyclic subgroup of order n. The denominator, I think we know, the number of generators for each cyclic subgroup of order n will be phi of n, where phi is the Euler's phi function. It is given by total number of elements of order n in G by phi of n. What is phi of n? The number of generators for each cyclic subgroup of order n, where phi is the Euler's phi function. Agreed. Now we will apply now here. Now the number of cyclic subgroups of order 11 in Z11 plus circle Z11 is equal to total number of elements of order 11 in Z11 plus circle Z11 divided by the number of generators for each cyclic subgroup of order 11. The denominator is phi 11. Phi of 11 is prime, it is 10. Now how many elements of order 11 are there in Z11 plus circle Z11? Out of these 121 elements, one element is of order 1, that is the identity. And the remaining all elements of order 11. You can check. You take any ordered pair A comma B, it's of order, and which is not an identity, is of order 11. So the total number of elements of order 11 in Z11 plus circle Z11 is 121 minus 1 by phi 11. That is 120 by phi of 11 is 10, that is 12. So the number of cyclic subgroups of order 11 in Z11 plus circle Z11 is 12. So how many subgroups of order are there? It will be 12 subgroups. There will be 12 subgroups of order 11, I can say. So there's the option, the revised option 4 is true. 4 star is true. So that means here, how many are there? For that there is a formula I wanted to tell you. For that reason, I have revised my one of the options. So remember such formulas and prepare a list of formulas, the number of so and so, the number of groups, number of subgroups, the number of generators, number of abelian groups, and so on and so forth. The number for in algebra, the number of so and so, you will get. Prepare a chart and get ready for the examination. With these few words, I say, I am sure that you have understood the solution of this problem. I thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We will meet you once again in another episode of learning. Enjoy learning mathematics, and I wish you all the best. Thank you.